Okay, so yeah, it would be a nice way to conclude this course by telling you the route to quantum factoring, basically, right? So we have pretty much all the ingredients in place. What we need to understand is this order finding a little bit, and then that's pretty much it, because that forms a critical subroutine of the factoring algorithm, right? And as you will see, the rest of the steps of the factoring algorithm are all classical steps. The main quantum step and the quantum speed up comes from order finding, and the sort of clever trick that is used here is that the order finding is converted into a phase estimation problem, and phase estimation becomes exponentially faster because of the factoring algorithm. Sorry, the Fourier transform. Sorry. Yeah. Okay, so let's recall what order finding was. So the problem was to find the smallest r. So given two co-prime numbers x and n, so everything is positive integers here, with x being much less than n, let's say. Then find the smallest r again you want to find the smallest positive integer r, such that x to the r is 1 modulo n, right? So we discussed some aspects of this modular arithmetic, etc. yesterday, and we saw how we can argue that this r is something that lies between, it's something that's strictly less than n actually, right? This is something that can be shown. First of all, we can show that there exists such an order and that it is less than n, right? So let us say that we denote the number of, so the first thing is to parameterize. So you notice that the notation becomes slightly different here. Normally we denote capital N to be the number of bits, or and stuff, at least in the factoring, in the Fourier transform we denoted it like that. But here L is going to be the number of bits that you need to represent N, right? So what I'm trying to say here is that this is essentially the number of bits needed to specify this number N, right? Then we consider an L qubit system, right? So we are working with an L qubit system, and we consider an L qubit unitary. Whose action is as follows. So this unitary is defined for a given x and n, right? That is given to us in the problem. It acts on any computational basis state. Y is, of course, something between 0 and 2 to the L minus 1, right? This is the set of all L bit strings, right? And so the numbers that it will correspond to lie between 0 and 2 to the L minus 1. In other words, it lies between 0 and N minus 1, right? What this is going to do is it's going to multiply each label Y with X, and this multiplication is carried out modulo N, right? So first of all, like I said, what tells me that this is even a unitary, right? So let us note a few things about this kind of a transformation. So let's say that we can define such a transformation, okay? So suppose we have two different, suppose we act this on two different basis states, right? So suppose we say u xn acting on y is xy mod n, acting on y prime is xy prime mod n, okay? So the first thing I want to show you is that these two are distinct. So its action on distinct computational basis states is distinct. Okay. So let's assume the contrary first. So suppose these two were the same, that is xy prime mod n is the same as xy mod n, then that would imply that x y prime minus y mod n is 0 mod n, right? Which would then mean that these two must be equal. Y prime must be equal to y mod n. So the point is that the action of this u, which is parameterized by x and n, on distinct, so let me say it this way. So the action of this is to map each basis state, and by basis I of course mean the computational basis state, to a distinct state. Okay. So this is the first thing to note about this. Now, what are these output states after the action of this unitary? So x is also some positive integer, right? So when I multiply xy modulo n, what would I get in this label, in this sketch? So obviously this is also some integer between 0 and n minus 1, right? So the output states essentially also belongs to the same set, which is 0, 1, etc. up to n minus 1, which is the same set 0, 1, etc. 2 to the n minus 1. So then what are we saying? We say that, so essentially this u is mapping you from this set of computational basis states to the same set, right? So what kind of a matrix is this, or what kind of a transformation is this? This is basically just a permutation. So it maps distinct basis states to distinct basis states. That's what the first thing tells us. And now you note that the output is nothing but one of these computational basis states also. So it's mapping you from this set to this set in a distinct manner. So the only kind of transformation that does that is a permutation matrix. And so these two steps basically then tell you that U is of course a unitary. And what is more, it's a special kind of unitary, which is a permutation. It permutes the basis states, right? It is simply, the action of this unitary is to simply permute the basis states. The next property that we will note is that this has an interesting relationship with the order of x and n. So what is u squared acting on y mod n? This is x squared y mod n, right? And so on and so forth until you realize that x to u to the r, well, I don't need to put mod n for y. Y is anyway something between 0 and n minus 1. So u to the r acting on this is x to the r y mod n, which is nothing but y, right? And this is true for all y, which belongs to this set 0 to 2 to the n minus 1, which means that u to the power of r is identity. So this is how the order comes into play here, that if r is the order of x with respect to capital N, then the corresponding unitary is idempotent, which means some power of this unitary is identity, and specifically the rth power of this unitary is identity. So now what can you say about the eigenvalues of this unitary? So the eigenvalues of u, what can you say about the eigenvalues of u? Are people around?
Rth roots of unity.
Indeed. So the eigenvalues of U must be the roots of unity, specifically the rth roots of unity. These eigenvalues are pure phase, right? And we know that the rth power of the unitary has the same eigenvalue raised to the rth power. And we are saying that the rth power of this unitary is nothing but identity, which means that these eigenvalues must be the roots of unity, right? So we can now actually write down what these eigenstates look like and then argue that doing phase estimation for U, remember the phase estimation algorithm does this powers of U, controlled powers of U, right? So then we can argue that doing that will actually reveal the order R. Okay, so let me just write down the eigenstate first and then we'll check that this is indeed an eigenstate. So the next or the last property here will be to note that the eigenstates of U are of the form. So remember, it's a permutation matrix. Now obviously these eigenvalues are some superpositions of these different basis states, but what kind of superpositions are they? So one can show in fact that the eigenstates are of this form. So I will just write down the eigenstate. So S is the label, right? So the eigenstates, I'm labeling them as U1, U2, etc. There should be UL of them, right? This is an L qubit unitary. Sorry, actually there should be. Yeah, so we'll see how many of them there should be. But of this, US specifically is of this form, that it is 1 over square root R, K going from 0 to R minus 1. Basically, you're cycling through powers of X mod n from 0 to the order, right? Because once you hit the order, you're again going to cycle through the same values, right? That's what we saw already. So e to the 2 pi I is K by R. Minus sign is more like a matter of convention, but yeah, so this is how these eigen states are defined. So how many distinct eigenstates do we have? So I can have S is 1, 2, 3, 0, 1, 2, 3, etc. up to
minus 1.
Huh? What minus 1?
R minus 1.
Okay, so let me label these now as 0. So I want to say that there are R of them. So let me label them as U1 to UR minus 1. Okay. So there are R distinct eigenstates, and I have to still argue that they are eigenstates, but that is now easy to check. So we can check that these eigenstates, that these are indeed eigenstates. You act U on US, right? So what do you get? Please work this out with me as far as you can. So this is just going to add one more power of X, right? So this is xk plus 1 mod n. So now it's a matter of relabeling things and pulling out a phase, right? And then this simply becomes US again because it cycles through, right? So what is the phase that we have to pull out? You pull out an e to the 2 pi I s by r, right? Then you will notice that what remains is simply ket US. So since I pulled out one, I have to add one more. So this becomes S k plus 1 by r x to the k plus 1 mod n. But this is nothing but ket US again because this is all cyclic. That's it, right? So the order comes out in the phase, right? So the phase of the eigenvalues are of the form S by R, right? Where S itself goes from 0, 1, 2, 3, etc. up to R minus 1, right? So the route to order finding is to basically run the phase estimation circuit to obtain the values S by R for different S, and hence obtain R. So there is again a fair bit of number theory involved in this last step, which is that if I do estimate using the phase estimation, if I get S by R, from there, how do I get to R? There is what is called a continued fractions way of doing this, that you're taking this, this is going to be some rational number, S by R, right? And there is a way to do a continued fractions expansion and hence get to the value R. Okay, so we will not get into that again. So all of this is, of course, chapter 5 of Nielsen-Chuang, like I said. So I referred you yesterday to the error and performance analysis of phase estimation. That was section 5.2.1. So if you look at section 5.3, that is fully about order finding, and in particular it will tell you some details about this modular arithmetic also, which is there in the appendix, and also this last step involves a continued fraction expansion. Again, I don't want to get into that because then I will be doing at least one lecture on number theory, which I don't want to do now. So those of you who are interested, I will let you go and look it up. So yeah, so this would be section 5.3 of Nielsen-Chuang, right? So this pretty much is I mean, this is the key quantum idea here, right? That you're defining a unitary which whose which, you know, in a way that the eigenvalues of this unitary are basically the rth roots of unity, and using that and using the fact that you can estimate the phase of these eigenvalues efficiently using a quantum circuit, you're arguing that one can do order finding efficiently using a quantum circuit. So let me just outline the algorithm. So like I said, the details of this algorithm are left as one of the assignment questions for you in assignment 4. I hope you all saw my message that I'm making assignment 4 optional. I will take the average of the best 3 out of 4 assignment scores, right? But although it is optional, I strongly advise you all to work through the assignment because it has some interesting questions. It has a question on quantum counting. That is, someone asked me this question in class, right? How do you know how many solutions there are? So that you can use a counting algorithm before you do Grover search in a search problem to know how many solutions there are for a search problem. And it also involves some of the details of the order finding algorithm. Work through that problem just to, it will help you understand even phase estimation better if you work through it, right? So what are the key ingredients that go into the order finding algorithm? So this is similar to phase estimation, right? So we already know what we need to do. So we have one, so let me just jump directly to the algorithm. So you have a t qubit register, that's what we said. right? So this T now again tells you to what degree of accuracy you're going to estimate the eigenvalue, which in turn will determine to what degree of accuracy you're going to estimate the order, right? Okay, so this is a T qubit register, right? And then you end up doing a Hadamard tensor T, right? And then you have this, all these controlled unitaries acting on the ancilla. But now hold on a minute. This ancilla is supposed to be prepared in the eigenstate US, right? So if you can already prepare the eigenstate US, then what is the need to even run this algorithm, right? So while the algorithm assumes that you can sort of create this permutation matrix. Now this permutation matrix can be jolly well created without knowledge of the order R, right? Because this only relies on knowing little x and capital N. Once you know that, you can define this unitary transformation, and this is simply a permutation of the computational basis state. So defining this unitary is no problem. Therefore, implementing it, for us, defining is as good as we have implemented it as far as this course is concerned. So implementing the unitary is no problem. Implementing powers of u is no problem. But what is a bit of a, chicken and egg problem is, what about this eigenstate US, right? Because this is the eigenstate corresponding to a particular eigenvalue. In phase estimation, we kind of brush this under the carpet and say somebody has given us this eigenstate U. But if I start an order finding algorithm and all the inputs that you have are only x and capital N, how do I prepare this eigenstate US? Right? So what you can do actually, turns out, is you don't need to prepare the eigenstate US. So this so-called ancilla register can actually be in a superposition of eigenstates. Okay, so the ancilla register need not be prepared in a particular eigenstate. What we can do is the following. So like I said, we assume that we can do these powers of u, right? Now that again requires a bit of working out to do what is called modular exponentiation, but that again can be done. But it does not presume knowledge of the order, but knowledge of the eigenstate US, because you see the way you're preparing US, or the way you've defined US, is a superposition like this, right? Which very much involves knowledge of R. And now I started by telling you that finding R is hard. So, how can you prepare this eigenstate US? So there is no need to prepare the eigenstate US. It turns out, and this is another key step, because otherwise this whole algorithm is sort of bound to fail. In the sense, it's not, offering you any speed up, because if you have to know R in order to even implement the algorithm, that's, kind of, that becomes ironic, right? Okay, so the point is, you can prepare the ancilla register in a superposition of the eigenstates. And there's a particular superposition which gives you a very standard ancilla state, and this particular superposition is a uniform superposition. So consider the uniform superposition, which means no phases, right? So 0 to r minus 1 US. And now it is left for you to check that actually, if you plug in this expression, which involves summing over all these exponential phases, so if you use, so if you use this expression star down there, right, and then you run the superposition over all these x to the k mod n's, with k running from 0 to r minus 1, then you can show that this is actually simply equal to a single computational basis state, the ket1, right? The ket1, which is the basically all zero string with just one somewhere, right? This is the all zero string with one n somewhere. This is the L bit string, right? So you can check using star. So it simply involves a bit of analysis using the roots of unity. You just need to know your roots of unity well and their property, right? Then you can show that this uniform superposition of the eigenstates is actually simply kept one, right? And it turns out that one can, so this was something which I did not mention during the, when I discussed phase estimation yesterday, but it turns out that using the phase estimation now on a superposition of eigenstates also works. Because even in the phase estimation, you can ask this question, right? How do I already have knowledge of this eigenstate? It's as if someone magically prepared this eigenstate and gave it to me, right? And that is somehow crucial for the algorithm. But again, it turns out that you can prepare this in a superposition of eigenstates, and you can get pretty much close to the same performance as the original phase estimation algorithm. So we can prepare this ancilla register in a simple state, namely the ket1 computational basis state, and then you do all these controlled unitary operations, right? And then you proceed with the phase estimation algorithm as usual, which is you do the inverse Fourier transform and then measure. So there is a fair bit of analysis now to show how this measurement is actually going to give you, first of all, that it gives you a phase which is close enough to the original phase S by R, and secondly, how to go from S by R to R, right? Now, I am not going to spend time doing that analysis. I would rather just outline the steps of the factoring algorithm in the remaining time that we have. But anyway, so that part is left for you to read up. Basically, it's like I said, that is mostly it's literally just analysis, right? Analyzing the errors and analyzing the probability of success. Is there anything else that I wanted to say about order finding? So yeah, this is the algorithm. This is the circuit, right? It turns out that this entire, so what is the kind of resources required? So it turns out that all of this can be done in order polynomial in L, right? Where L is basically now log N, right? So one can, so what does it require? It requires these T Hadamard's, it requires the inverse Fourier transform. It requires a bit of classical post-processing because you have to do the continued fractions expansion to get to, so let me just list the total resources that are required. So you need, so it turns out that you need order LQ gates to do the powers of U. Let me say the controlled powers of U. So the lambda U to the K operations. There is again a trick to do this called modular exponentiation. And again, I'm going to refer you to. Yeah, maybe if we had in-person lectures, I might have gone ahead and done a lot of this analysis, but in this online mode, I feel like we've already exhausted everyone's bandwidth. So let me not do these analysis here, but I'll refer you guys to the appropriate sections, and those of you interested can look up. But otherwise, you can take it from me that this is what the resources scale like. So remember, L is approximately log n, okay? Or the closest integer to log n. So then we need, it turns out, order L cube for the continued fractions algorithm. This is a classical algorithm which is going to estimate R given S by R, right? Where S is something between 0 and R minus 1. Well, the 0 obviously is not going to give you any information, but 1 to R minus 1. And then what, right? So what else do we need? We need to prepare this ancilla state. We need the T qubit register, but T is kind of determined by the accuracy with which you want to do the estimation. And then you have these T Hadamard gates, right? So that's pretty much it. So the entire thing is basically an order L cube algorithm, right? Just like how your Fourier transform itself was an efficient algorithm in this case, that it was something like n log n, right, instead of 2 to the n. Similarly here, this is log n cube, right? So this again created quite a stir because there is still today no known classical algorithm which can do order finding in using resources which are polynomial in n, right? But here you have a quantum algorithm which invokes classical subroutines like this continued fractions algorithm, which is a classical algorithm. But even including the classical resources and the quantum resources, this scales only polynomially. This scales actually log n, right? It scales polynomially in log n, right? So this is a huge improvement over what exists classically currently, right? Questions? Okay, so these missing steps of the algorithm, which is basically to show that if you have a superposition of the eigenstates, you can still do phase estimation. That's what is left for you to do in the assignment. So please work that out. I have indicated all the steps there. So I hope you can work this out, right? Okay, so the final step then is to look at factoring. But like I said, the ingredients are all already there, right? So we can simply write down the steps of the factoring algorithm. Again, yeah, if I had Blackboard lectures, there are times in the past where I've actually worked out and proved some of the number theoretic statements that are involved here, but we will not do that today. So let me just state the problem is given some positive integer n, find its prime factors. Okay, so this will typically be of this form, some p1 to the alpha 1, p2 to the alpha 2, etc., pm to the alpha n. So there could be m prime factors, p1, p2, etc., pm, and they could all occur with powers alpha 1, alpha 2, etc., alpha n. Right? So again, you will notice that much of this, the steps of this algorithm, most of them are classical. The key step which for which you get a quantum speed up is the order finding step, right? So I will not get into proving some of the theorems, but I will merely state the steps of this, right? So how does this algorithm proceed? So how would you typically find the prime factors? Well, of course, the obvious thing to do is to check whether the number is even or odd, right? So check if n is even. If it is even, return 2 as a factor, right? And then keep doing this until you exhaust basically powers of 2 and powers of 3 and so on. So more generally, you can say that if n could simply be of the form a to the b, right? Then return a as a factor. Turns out that there is a efficient classical way to do this, and the classical algorithm only requires order L cube steps or order L cube operations. So by the way, L again we will define to be log n. Okay. And then you pick some number between x and n minus 1 and check if the GCD is something non-trivial, right? So if the greatest common divisor is something which is not 1, then you can return that GCD as a factor. Basically, you're trying to get to a point where you now have an x which is co-prime with n, right? So the next step you proceed only if the first step is a no, right? So you keep repeating the first step until that becomes a no, and then you proceed to the second step. Then you check this and then you proceed to the next step. So now if you do have an x whose GCD with n is only 1, then you do the order finding step, right? So then use order finding to find r such that x to the r is 1 mod n. Now this order could be even or odd, right? Then there is a theorem which says that with high probability, if you have an x that is chosen uniformly at random and is co-prime with n, then with very high probability, the order r will be even. Okay, so if the order is not even, you go back, pick another x, and soon enough you will find an x such that the order is even. Okay, so if the order is even, and this happens with high probability, then as we said, you have x to the r by 2, so you compute the GCD of x to the r by 2 plus 1 and x to the r by 2 minus 1 with respect to n, right? And one of these two must be a non-trivial factor. And this is a key step because this is the step that will actually find for you a non-trivial prime factor of n. By non-trivial, I mean one which is not simply picking out powers of 2 or 3 and so on, right? Because you actually have a number that is co-prime with respect to n and you're finding the order with respect to n. And then either x to the r by 2 plus 1 or minus 1 should divide n, right? So you find the GCD of these two numbers and then one of these must be a non-trivial factor. So these are the steps, right? And if the order is not even, you repeat this a few times and then you will get an order which is even. And then by repeating this a few times, you're going to end up with all the factors of n, right? So once again, the performance of this algorithm, that you see the main quantum steps. So all the others are classical steps, right? So let me just mark out this. So steps 1, 2, 3 are all classical, right? And finding the GCD also can be done in order L cube, right? There is a famous algorithm due to, I think this is Euler's algorithm, which finds the GCD efficiently, right, between two numbers. So the finding the GCD is also efficient classically. So I remember correctly, this is order L cube. Right? checking whether n is of the form is simply a power of the form a to the b, that's also efficient classically. The key step, which was the hardest step classically, was the order finding, and that we now have an efficient quantum algorithm to do that, right? So this is the only quantum step in the factoring algorithm, and this step is as efficient as the other classical steps. So this also is of order L cube. So overall, the performance of this algorithm, or I think I've been calling this as resource scaling for the algorithm, is simply order L cube gates or operations, which is order log n cube. So that completes this entire segment where we started from the Fourier transform, went on to do phase estimation, then order finding, and then finally factoring, right? So questions? Okay, so this pretty much completes all that I had to say. We've also run out of lectures, so let me stop here.
Ma'am, I have a question.
Yeah.
I think I should have asked it a little earlier. So this order finding,
Mhm.
was it a specific application that is used in some maybe other algorithms, or I mean,
What do you just used it for factoring, but you're asking whether this is also useful for other things?
right?
Yeah, indeed. So there is something called period finding. This is also useful for period finding. There are, in fact, other approaches to doing factoring as well, okay, based on what is called a discrete log algorithm. But it turns out that at the heart of all of that speed up is the ability to do a Fourier transform of some form. Okay, so yeah, order finding does have other applications. The simplest of them is what's called period finding, but these are all basically number theoretic based applications, right? Like factoring.
Yeah, right.
Yeah, I again did not have time to discuss period finding, but that is another way to do factoring. I mean, it's sort of equivalent to order finding, but you can think of it as an application of order finding. Yeah, so there is, like I said, another route to factoring. So this approach to factoring and this quantum speed up is of course due to Peter Shor in 92. So around the same time, there was an alternate approach to factoring uh, by Alexei Kitaev, and this approach does not use this whole sequence. It does not do Fourier transform, period finding, I mean order finding, and this. It actually uses something called a discrete log algorithm. Nielsen Chuang does discuss this in some parts, but I'll see if I can post some other articles on this or Moodle, right? So it's a completely alternate approach to the factoring problem. But like I said, at the heart of it, the speed up comes from the ability to do something like a Fourier transform exponentially faster. Okay.
Yes, ma'am.
Yeah. So who asked me yesterday the question about the analysis of the phase estimation? Was that you, Siddharth, or uh,
No, ma'am.
I had asked it, ma'am. Amog.
who's this? Amok. Okay, hi. So yeah, I can quickly tell you, since we have a few more minutes, I can quickly tell you how to understand that. Let me stop sharing this and share yesterday's file itself. Okay, so let me just add to this file from yesterday itself. Yeah, so the question was about the performance of the phase estimation algorithm. So what we discussed was the ideal case where this phase phi, which as we said is some real between 0 and 1, has an exact t-bit representation. In the sense, this can exactly be written as 0.51, 0.52, etc., 5t, right? This is what we discussed. Now, in the actual case, let us look at the final state after the controlled unitaries, after all the lambda u to the k operations. So phi is the e to the 2 pi I phi is the eigenvalue, right? So what we are going to get is this state, right, which we wrote down as superposition of this form. Where is this? So we wrote this down as a tensor product, but I'm going to now collapse the tensor product back into a superposition. So remember, we did this when we did the Fourier transform analysis, where we went from a superposition of the L qubit, the rather n qubit states, to a tensor product form where each qubit was locally in a superposition, right? So here this is e to the 2 pi I 2 to the t minus 1 phi, etc. Right? So this is the tensor product form. Now I can write it again as a superposition of all the computational basis states of the L qubit system, right? So this is now rather T qubit system. I keep going back and forth. Yeah. So this is 1 over 2 to the T by 2. K going from 0 to 2 to the T minus 1. 2 pi I phi k ket k, right? So this is some weighted superposition of all these T qubit basis states. Now you do the inverse Fourier transform on this. Okay. So the inverse Fourier transform is going to now add another, so there's going to be a sum over some other j index, which also goes from 0 to 2 to the t minus 1. Because remember, now you're doing a Fourier transform, or rather the inverse Fourier transform, on this T qubit space, right? So this is e to the minus 2 pi I jk by 2 to the t. This is the standard Fourier transform expression, j, because each k becomes a superposition of this form, right? And then there's a sum over all these j's. Now the claim is that if this was exact, suppose phi had an exact t-bit representation of this form, then this, whatever we wrote down yesterday, can exactly be written as these fractional powers of phi, so that each phase pulls out one significant bit in this binary expansion. But that is assuming that this is an exact representation. If it is not an exact representation, this is the best you can do. This is what you have. Now the task is to somehow extract phi from this, right? So this is the state post the Fourier transform, and now you're going to measure, and you're going to measure in essentially the computational basis of this T qubit space. So when you measure, what the analysis tells you is that so when you measure, you're going to collapse onto some T qubit basis state, right? And these Weights will tell you what those amplitudes are, right? So the probability aspect comes from this. This entire sum would collapse into a single computational basis state with simply phi 1, phi 2, etc., phi t as the t labels, if this was ideal. But in the actual case, this need not be exactly equal to phi 1, phi 2, phi t. This is going to be some t qubit state. If I view it in the computational basis and I measure, I have some probability of getting any one of these 2 to the t minus 1 basis states at the as the post measurement state. But what the analysis tells you is that this t qubit basis state that your measurement will collapse to is with high probability this state, this post measurement state, will be close to, or rather, well, it gives you, yeah, let me just say it's close to phi. Okay. It gives you a bit string. Let me say this is post measurement state is something like this, B1, B2, etc., BT, that it will be close to this T bit string that you want, right? And the two parameters that are therefore present in this analysis are how close are these two. So there is an error tolerance that you have to fix, right? And that fixes the probability for you. And the error tolerance also fixes for you how many bits you need, how many qubits you need in your data register. So this is what I stated yesterday, that estimate this accurate to n bits. So that means that this error probability is bounded by something like 0, it's between 0 and 1 over 2 to the n, right? That's what it means to say that it is accurate to n bits. And you have a probability. The probability of success will be determined by these amplitudes. So you have to do a bit of analysis of these amplitudes and put a bound on that, and that will bound the probability of success, right? So if you need a probability of success of 1 minus epsilon or a probability of failure of epsilon, then you need t qubits where t goes as n plus log 1 over 2 epsilon, roughly. Okay. Is this clear, Amok?
Yes,
Where
ma'am,
this,
yes.
where this probability aspect comes from, because you no longer have a single, the way I describe the algorithms as if there's a single t qubit state that you get after the inverse Fourier transform, and that exactly matches. Of course, that happens in the ideal case, but you're not going to have an ideal t bit representation for this. So this is where the probability aspect comes from. Okay.
Yes, ma'am. Thank you.
Yeah. Okay. All right, so good luck for the NSEM. And like I said, the NSEM will be a closed book. I trust all of you to follow the honor code and do the exam honestly. You will have enough time to work out, to scan and upload. You are allowed to write down any expressions, formulae, anything that you want in one sheet of paper and only refer to that during the exam, right? No Googling, no nothing else. No looking into your textbook or your notes or my lectures. Although I think all of that will only distract you from the exam, it's better to just sit and work it out. Okay. Any other questions? Yeah.
Ma'am, in the expression for the error probability of this phase estimation, is it the natural logarithm with base e?
Um,
Ma'am, that t equals to n plus.
No, I think it's log to the base 2 only. This one, right?
Right.
Yeah, I think it's log to the base 2.
Okay, ma'am.
Okay, so I may see some of you next semester if you have enrolled for the advanced QC QI course. So some of the things which I did not get to cover in this, I will probably cover in that. So for example, of course, I've not told you why factoring is such a crucial problem and why Shor's algorithm created such a stir and got everybody interested in quantum computing. So that has to do with some aspects of cryptography, which maybe I will do in the next semester's course. But otherwise, I'll be primarily focused on decoherence and error correction, and also some aspects of quantum Shannon theory, quantum information theory, which we did not get to do in this course. Okay. All right. All the best, and I'll see some of you next semester.
Thank you, ma'am.
Bye.
Thank you.